detection based on GNSS's signal strength measurements.
Okay, pressure's on the chair, so let's get us back on time, eh? Right, okay, let's go. Forest change detection based on GNSS signal strength measurements. So, what we're talking about here is satellites or aircraft flying along, looking at the ground and looking at reflections of GPS signals from the ground and using them as an observation parameter. So, a little bit about motivation, a little bit about method, and an experiment and results. No surprises there in the outline. Okay, so, motivation. Why are we using the signal? Well, one nice thing about using GPS as a radiator, right, is that it's everywhere, it's free, and you don't have to provide the signal. So, if you're talking about flying on a satellite, it's not like having a radar where you need a lot of power to power a transmitter. You just need a receiver, which uses far less power. So, it's actually quite a nice, it's a nice setup if you can make it work. It doesn't cost you very much in mass, and it doesn't cost you very much in power. So you can actually stick it on relatively small satellites, and we're actually talking about trying to get this on CubeSats. And in the same way that I referenced this talk in my CubeSat session, I can refer back to there's a CubeSat presentation I did in the last session. And there's also the motivation of looking at forests. So we're using, there's the signal, what should we use it for? Let's look at forests. Forest change detection was actually a project that we looked at in our SAR. The same project that funded this work funded some SAR work, and we looked at forest change detection there, which is sort of where we got the idea from. And you know, the idea is that change detection is useful for forests in situations like if you're doing REDD, you're trying to keep the forest from being logged. If you're able to detect a road being put into the forest, you might be able to stop the loggers getting in and deforesting and so on. So there's all sorts of reasons why you might want to use this for forestry. So what happens is the platform flies along, and this same method actually has been used on stationary receivers, so like a big pole looking down at the ground. Not particularly useful for forestry, but so for the forestry application, we would look at a moving platform, aircraft or satellite. This is a correlation. So what happens is, in the GPS receiver, signal comes down, and you use the correlation to work out how far away the satellite is. It's part of how GPS works, right? So even another nice thing about this application is that you're basically doing, in the GPS receiver, what you were already doing anyway. You're not really doing anything too special about the signal processing. So you work out the delay from the satellite directly in the direct line of sight, and you look out the delay from the reflected signal. Now, this delay, you can use that to do altimetry, that sort of thing. The distortion of this reflected signal you can use for measuring wave height on water, wind direction on water, that sort of thing. We're trying to use it for soil moisture, a bit more complicated. But you can see that the shape of that is actually slightly different to that, and the change in shape is helpful in some of those applications. Now, for this application, what's interesting is this height, or the height difference between those two, right? Okay, I've got a nice picture somewhere. These are not my slides, by the way. If it was me, I'd put lots more pictures in. I wouldn't have words. I just sort of feel. I do the words, that can do the pictures. Anyway, okay, so how do we detect? So, line of sight coming down, we've got one antenna looking upwards. The signal coming from the GPS satellite is right-hand circularly polarised. It hits the ground, and so it becomes back left-hand circularly polarised. So, looking up, we've got a right-hand antenna. Looking down, we've got a left-hand antenna. And I don't think there's anything interesting here. We can colorise it, as you'll see in the pictures. Yeah, so we're looking at the peak powers in this particular case. Yeah, there's nothing on that those words there that I'm going to show you in a picture in a minute, right? Okay, so what has happened over the course of our project, we've actually run 4 experiments. So we've run a couple over the sea, we've done a couple over the land, looking at reflectometry. So we've flown the US UNSW aircraft. This particular experiment we're talking about now was run last year. And we flew over southwest Sydney and around the forests there. And there's the 2 antennas, that's it. That's very definitely a plane. That's the receiver, right? Now, so what we've done with this receiver, we've got one plug for the antenna looking up, and for the experiment we're just about to discuss, we have another one looking down, the left-hand polarized looking down. If you wanted to do something else on the soil moisture, for instance, you would have a third one, which you would also face down, right-hand circle and polarized. So you look at the difference between those polarizations to infer some information about soil moisture. But the nice thing about having this multiple front-end receiver is it's synchronized, right? So the channels in here are being sampled at the same time, and so it's actually really easy to do that delay measurement, because you're not using 2 GPS receivers trying to synchronize them using GPS. The synchronization is done in the receiver. So this multiple front-end thing is really quite useful. So that's the antenna that lives on the plane anyway, looking up. This is our antenna looking down, and in fact that antenna has both left and right polarizations on it, so really to get those 2 inputs you just have 2 plugs and 1 antenna. There's the track. So welcome to everybody to Melbourne in the middle of winter. You know, there are warmer places in Australia, and here's one, Sydney. For those of you that don't know, there's a lot of rivalry between the 2 cities in Australia, the 2 major cities. So this is our this is sort of like our small aircraft airport out of Bankstown. So you fly out there and flew around, and then I don't know what this is about, do a few loops, back again. But what we were able to do is cover suburban areas out here, farming, a bit of farming, farmland here, forest, quite dense forest out here, cliffs and everything. For those of you that have seen pictures of Blue Mountains, quite rugged territory. A little less rugged territory here over the national park, second oldest national park in the world, and then back to Bankstown. So that's the route they flew. The data we're looking at is between points A and B here, and that's one satellite, right? So it's satellite number 31. The GPS satellites go from 1 to 32, so you won't get numbers higher than that. And you can see that as you fly along, there's changing responses, which is nice because we can actually start looking at things. Then you start putting colours on there, and I'm pretty happy with this. I mean, I was the project leader, right? I didn't do anything useful, I still don't do anything useful, but I'm happy to talk to you about this stuff. This impressed me greatly. I'd never seen a picture like this of this particular stuff before, so I was really pleased. So, flying along, you can see the sort of weak colours are orange, strong colours are bluey, purple, and then green, and that is in the middle, right? So fly, 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 you come over the forest, it's weak, you come over this cleared land, it's moderate, weak, moderate. And this area here, you probably can't make it out too well in the picture, but there's a big line of cliffs here. So the signal there is being attenuated for some reason, but it's probably to do with those cliffs. Then once you get over this water, this is the main catchment of Sydney, you're getting a nice strong response. Once I saw this picture, I thought we had something that we could work with, right? So let's zoom in. So now you can see one of these cleared areas that we flew over. So there's the track of the plane. So looking directly down from the plane, it makes that blue line. And then the other one is the reflection, which is always going to be a little bit off to one side or the other. Again, you can see sort of weaker returns over the trees, and a stronger return over this cleared area. So if you're starting to think about trying to detect changes to the forest or areas that have been cleared that you want to pick up, in the same way that SAR works at night and through cloud, so does this. So if you're trying to find things in rainforests that are very cloudy, you can use this method. You don't have to use optical. Here's another one and you can see there's actually really quite a strong return from there. That obviously something they've cleared has made a big reflector there, which has given us a nice return. But again, you can see that the boundary, almost infeasibly, if you're talking about, I think this is just Google Earth data, lines up very nicely with these edges of the forest. There's one over the water, just to show you the very strong returns we get over water. Nice specular reflections. Probably not as, a bit stronger here. So there's probably rocks, I think, under those trees, which are giving you a bit better reflection, and so on. So just a few examples. Now, this is the same flight, but looking at all the different satellites. So, when you're flying your GPS receiver, you could actually get up to 12 satellites at a time. It's a restriction on the receiver rather than the system. And you can see that even without, this is fairly raw data. We have not normalized this data for the antenna pattern of the receiver, the antenna pattern of the transmitter, which is the GPS satellite. At different angles it has different receive strengths, or the reflection of the ground, because as you can see, it's very up and down, very hilly. So it's not a specular reflection you're getting, or it's not a flat surface. It reflects at different angles at different points. So when you get a cluster of these, you can see that the cleared areas really come up quite nicely. And even without this normalization, which we still need to do on this data, even though this was taken, actually this processing was only done relatively recently, even though the data was grabbed last year. You can see there are regions, even in the forestry, which are darker and lighter. And I think that by the time we normalise this properly, I think we'll be able to do some pretty good classification on this stuff. So as far as detecting, clearing of forests, it actually doesn't seem too bad. And you don't really need to do anything, right? You can do this without being detected in a way. You can do it in a UAV, and so on. So I think it's actually quite promising work. I think at the moment it's fairly early days, but certainly what we're seeing there is quite nice. We do have a PhD student working on this, and I imagine that the data we're presenting at future events will be much more impressive than this. But I just like the picture; it's so colourful. Okay, so although this is fairly early work, I think it's quite promising in terms of what we're able to do. I think we should be able to do classification. It's a different type of classification. And the other thing I guess I need to mention is that this plane was flying fairly low. So if the plane was twice as high, if the plane was twice as high, the width of this band would be twice as wide. So you can actually improve your swath simply by flying higher. Okay, so conclusion, it's a relatively promising area, and we will probably have some better results soon. I think it could be quite useful for monitoring forests. That's it. Thanks.
Thank you. Any question?
I'm pretty loud. Have you tried pointing the receiver sideways and get ranging information?
Well, you don't need to do that. I'm not sure really what you're asking. If the signal reflects off the ground and you range on that signal, effectively what that is used for is altimetry, right? So you can work out, due to the geometry, how high you're flying or how high you are above the ground. You don't actually have to point the antenna. Most GPS antennas are omnidirectional anyway. So a perfect GPS antenna would be semi-hemispherical or something. And most of them approximate that relatively well. I'm not sure if I got what your question was about.
I'm just curious if you basically simulate a SAR system with this just by pointing it, get it not omnidirectional, and point it sideways and get ranging information.
Well, most of the satellites that you are receiving from are at angles, 45 degrees or so. The lower they are, low angles is good and bad, because the lower angles have weaker received signals, and you are starting to roll off in your receive antenna, but the reflection's better. You get a better specular reflection. So you sort of do gain a bit. So you can actually receive signals from relatively low angles. Reflection. Oops. You have to ask this. He's doing time for the moment, and then I'm about to introduce the next speaker. What do you think? So.
But I still need to.
I agree that the contrast between the forest and the forest is very good. I ask you, are there information about the biomass? Have you tried to compare forests with different biomass?
Yeah, nice question. Just for people who didn't hear, he was asking whether we could use this for biomass. In the same way that L-band radar can be used for biomass, sort of, we think we may be able to get some information along those lines. The problem, one problem, is that you're not using, like a normal radar is monostatic, right? So you send the signal out and you receive it along the same line of sight, whereas this is a bistatic arrangement. So the phenomenology of the reflection is different. We're not yet looking at biomass. We'd be happy to do it in the medium term. We've got a couple of, we're actually going to move on to soil moisture next, but it's an interesting area which we will look at in the future. Still got time for another?
Okay, so you move on to next.
Move on to the next speaker. Who could that be? Oh. Okay. I'd like to, after having been introduced